School, okay? Next year, we will do it more lively, but we will try to do our best to do it as lively as possible. So you have learned a lot standard model physics, and now we are gonna really look and understand how these things, how these all theoretical ideas are found in reality, okay? So today we have two brilliant and very young experimental physicists, famous, and really with a long career, even though they are very young. First of all, we will hear from Jesus Puerta-Pelayo. Jesus Puerta-Pelayo is an experimental particle physicist. He has been working at CERN experiments during all his outstanding scientific career. After performing a research stage at Delphi, he completed his PhD at the CMS detector, focusing on the muon spectrometer. He has enjoyed an INFN postdoctoral fellow, as well as a CERN postdoctoral fellow, always in the CMS framework. He was the maximum responsible for some crucial devices of the CMS muon detector. Currently, he's a research staff member at CEMAT in Madrid, where he keeps his long-standing expertise at CMS, and pioneers also calorimeter studies for the future and highly ambitious ILC experiment. Last but not least, Jesus has an incredible trajectory in outreach and dissemination, devoting plenty of his little free time to these very important activities. And he really is a dog lover, and he is really taking care of dogs. Now I just learned about this, among other very nice activities. Secondly, we have sorry, I'm gonna mute some of you that you, yeah, okay. Secondly, we will have Bárbara González Álvarez, another experimental physicist. Bárbara got her PhD in particle physics with the University of Oviedo for the unique and excellent work she did on the search for the Higgs boson, precisely associated to a W boson at CDF, the collider detector at Fermilab in USA. After that, she worked as a postdoctoral researcher for Michigan State University and as a CERN fellow at CERN at the Atlas experiment. Currently, she's working very hard and highly successfully as a researcher for the CMS, also experiment of CERN, at the University of Oviedo, focusing mainly on the longevity activities of the drift tube detector for the high luminosity LHC, and on top, Higgs and standard model analysis. Barbara is also a super mother, an excellent tango and flamenco dancer, a professional swimmer, a golf player, and a high-tech runner. I don't know how can she do so many things simultaneously so well, but she manages. So, okay, so let's start with Jesus. Jesus, whenever you would like, you can start to tell us about CERN experiments.
Thanks so much, Olga. Thank you very much for this wonderful introduction. I am flattered, and I am especially happy that you call me young. I'm not sure that.
Well, I am young, so you are younger.
Okay, okay. Let's leave it like that. But it always makes me happy to hear people call me young. Okay. Anyway, so hello everyone. As Olga already introduced myself, I don't have to go much more in details into that. It is a pleasure for me to be here. It's a pleasure being invited to introduce you to the wonderful world of CERN in this school. I hope you're enjoying your lecture so far. Today we're going to be a bit more relaxed, and I hope I can give you an idea of what working at CERN means and all the projects that are being developed there. At this point, you're all fellow researchers, so it's almost insulting. It would be almost insulting for me to assume that you have never heard of CERN. Of course, everybody knows what CERN is. Everybody has an idea what at CERN is being done. But I will try to give you another view and some more details that maybe you're not so well aware of. CERN is a public research institution, and the acronym CERN stands for European Council for Nuclear Research. It was founded almost 70 years ago, so in a few years we'll be celebrating the 70th birthday, which is It's quite an achievement for a laboratory. The acronym, as I said, is European Council for Nuclear Research. Back in the time when it was founded, it was shortly after World War II, and the European countries decided to create a lab unifying all research effort towards nuclear physics. Nowadays, of course, our knowledge of the world goes far beyond the nucleus. So the CERN is commonly known as European Laboratory for Particle Physics, and it's the largest in the world nowadays. It's actually like home of half of us, half of the particle physicists working in the field. As an international collaboration, I think is an example for many other projects in this kind, because it's practically everyone in the world who's in the business of particle physics has some kind of contact with what's it's being developed at CERN. Currently, we are 23 member states, all of them European, because that's part of the constitution. 3 more associate states are in pre-membership status. Not 3, actually, 1 more. We are 4 associate states that are planning to join the council as members. Latvia signed just yesterday. 6 more associate states, of course, Japan, Russia, the US. As you can see in this map, practically everyone in the world has some kind of contact with CERN, and things work. That's surprising. So that's an example for many other projects of this kind. What do we do at CERN? CERN is mostly known as an experimental lab. So we do research, and experiments, mostly based on accelerator physics. But that's not everything that is being done at CERN. Not exclusively these topics. Of course, there is a large theory division that it's top of the class in the theory world. I understand many of you are theorists, so it's a good place to develop your scientific career in the future. Of course, technology is a very important part. The development of detectors and the development of technology for new accelerator, medical physics, technology transfer to other fields, and so on. That's a large part of the commitment of CERN. And education and communication are also very, very important, and because the science has an importance, but letting the world know that we are doing and how this is going to improve their lives is also a big part of a scientist. It should be. Let me copy here those 3 sentences that are the official statement of CERN, of what the CERN mandate is supposed to be. It provides a unique range of particle accelerator facilities for research. That's, of course, the main topic of CERN. Also, all the research in fundamental physics, not only related to particle accelerators, but also in other fields, and unite people from all over the world to push the frontiers of science and technology for the benefit of all. It maybe sound a little cheesy, but it's true. It's true. This kind of activities are really well taken care at CERN, and that's an example also for outreach and communication projects. But enough sugar. Let's get down to business. What is CERN? You all know where CERN is. CERN is close to the Swiss city of Geneva, but most of the CERN site is on the border between Switzerland and France. You see here these 2 the pink triangle, the pink square here. These are marking the sites where the main places where CERN is. One of them, as you can see, is totally inside France. This is the ring of the particle accelerator, the LHC. As you can see, this is very close to Geneva, the Alps. You can see early the Mont Blanc here, Lake Leman, and so on. And in this picture, you will be able to see CERN from the other side. So these mountains are not the Alps, these are the Jura Mountains. So this picture is taken from the other side. And this is an aerial view of the main CERN campus, what is called the Meran site. So this is supposed to be a CERN visit, right? So let's use Google Street View, and let's use some other tools to try to give you an idea of what walking around CERN would mean. Let me take this here, okay? This is what we're going to do now. You can do by yourselves on your own whenever you're bored at home and want to walk around CERN. This is the same view that I have shown you before, the same picture. As you can see, this is the main CERN site. These are the Jura Mountains. If we zoom out a little bit, you can see that I wasn't lying. This is close to the city of Geneva, Lake Leman, and so on. Let's get back there. I'll try to go slow. I know that the connection at Zoom sometimes chops the image of the video, so I'll try to go a bit slower than I usually go. So this is what people see when they reach CERN for the first time. Actually, this picture is, these images are quite old. This is when the globe was being assembled. The globe is this structure here. It's a pavilion that is installed right outside CERN. It's used for exhibitions and seminars and so on. And let's also use Google Street View and drop this little guy here at the main entrance of CERN. And I will show you, oops, where are you? Here. What's going on? Should work. It should work. Maybe it's the mouse. Was working before. Let me do something very fast. Here. But maybe it's because of the mouse. No? Sorry, then you're not going to be able to see what I wanted to show. But you can see it from here. I'm not going to lie to you. The first time one reaches CERN, it's a bit disappointing because what you see here it looks more like an industrial site. It's just like gray buildings and workshops and ugly pavilions and stuff like that. But as many other occasions, what it's important is not what it's outside. It's what it's inside, and even more what it's underground. Let me try again to drop this little guy here. No, maybe reloading the page will be easier. I think we have a problem with the connection. And try again. Okay, finally. So this is what you see. This is what you see. So you can see it's not the place you will want to visit. These buildings are pretty old. It hasn't changed much in probably 40 years or so. But what you don't know is that inside some of these buildings are some of the most important research facilities in the world. For instance, this large building here is an area in which the lines of the proton synchrotron of one of the CERN accelerators are conducted in order to do some interesting experiments. If you visit CERN as a visitor, you can also enjoy some of the exhibition halls. And so in some of them, for instance, here, there is a little garden here. It should work. The connection is not very stable, so I'm not going to be able to show it to you because it's going to take quite a long time. Anyway, you have seen the surface, and if you're disappointed, I wouldn't blame you because it's nothing so interesting to see. But CERN is mostly known for its accelerator complex, which is the largest and the most powerful in the world. You all know about the Large Hadron Collider. We'll go into detail into that. It is this tunnel that is sign in green here, but there are many more, and you can see the rings marking some of the other accelerators. These are the two lab sites that I was showing you before. And in more detail, this is a schematics of the CERN accelerator chain. You can see that the accelerator works in a way that you have one of the first stages of acceleration makes the particles reach a certain energy level, and when it's reached, it launches it into the second stage of the accelerator chain, and so on until it reaches the maximum energy that it's currently in the LHC. As you can see in this drawing, some of these accelerators are really old. The proton synchrotron, the PS, for instance, it was built in 1959. SPS is 1976, which is my age. So as Olga said, this is not so old. It's a young accelerator, and this we will see in more detail. The Large Hadron Collider is the largest one, is the largest ring, and it's CERN's flagship project nowadays. It's a collider of proton-proton most of the time. The maximum center of mass energy it can achieve is 14 tera-electron volts, and it's 37-kilometer ring that is underneath the surface at an average of 100 meter deep, and it makes beams collide in the experiment in certain collision points every 25 nanoseconds. This is what I was telling you before. So this is a video of how this chain of acceleration works. So the booster dumps particles into the PS jumps into the SPS. The SPS by itself was a very important accelerator. For instance, the W and Z bosons were discovered there when it was the largest accelerator at CERN. But from the SPS, the protons are launched into the Large Hadron Collider into parallel beams, and these two parallel beams conduct the beams of protons up to the collision points. You will see how this in this beautiful video, you will see how the beams of particles are led to the center of the experiments where they collide. They produce an avalanche of particles that are measured by the different layers of the detectors. But this is something Barbara will tell you about more in detail. I'm not gonna tell you any more about this, so we can go to the next. From the technological point of view, LHC is a very, very complex machine, but from the conceptual point of view, it's really simple. What do you need to make a particle accelerator work? You just need electric fields to accelerate the particles, and then you need some magnetic fields to keep them in the tracks you want them. So it's basically LHC, and all accelerators are a chain of electric and magnetic fields in order to keep the particles on track. This is a scheme of more or less what LHC looks like. If you look closely, it's not really a circle. It's like 8 straight sections here that are marked with these colors, and then 8 arcs. So it's a straight section followed by an arc, another straight section, and in the straight sections you have different regions where you can do different things. For instance, you have cleaning places, accelerate places where the beams are accelerated, dumped, and so. And in 4 of these points, the experimental holes, is where the beams cross and they collide, and then they produce the physics result that we expect and that you will hear from Barbara. Actually, we call LHC a particle accelerator, but the only part of LHC where particles are accelerated is this straight section. The rest is just to keep them where we want them or to make them collide. This is a picture of the superconducting dipoles that are used to bend the trajectories, and this is a picture of the radio frequency cavities used for the acceleration itself. Let's now take another walk underneath the surface, if Google Street View allows us to do that. First, we're going to enter CERN through one of these points. There are 8 entrance points to the ring. This is point 6, one of them. If we zoom out, you will see that it's right in the middle of nowhere in France. The CERN main site is it's even farther here. This is the CERN site I was showing you before, and point 6 is here. So you can see on the surface you have a lot of workshops and so on, but we can go to the tunnel. If we, I will add all these links to the slides in case you want to play with them and go take that walk that we're taking by yourself later on. We will enter through point 6. Here it is, and you can see this is a view of the tunnel of the accelerator. Here you see this is not the world's longest sandwich. This is a particle beam. This is the pipe where the particles go. And you can see here more or less is straight. If you notice that the line on the ground is straight. So we are in one of the straight sections. This will tell you nothing because it's just techie, a lot of cables, a lot of pipes, and a lot of services. If you, I cannot tell you in detail what each one of these components does. Some of them are magnets to focus the beam, some others are to clean, to achieve a monochromatic beam, to clean the energy of the particles that are straying out, and so on. But we can go a little farther and farther and farther. And at some point, we will reach the dipoles and we will reach the arc where the particles start bending. And this you can see clearly in the line on the ground, and you will be able to see it on the structure of the tunnel as well. You see, we are reaching that point. And I know that this is the arc starts here, not only because these are the blue dipoles, and we know that the dipoles of LHC are blue, but also because if you closely on the tunnel, then you can see that it's starting to bend to the right. Whereas if you look back, well, we are a little way inside the dipoles area, but in this area you can see clearly that structure of the accelerator I was mentioning before. About the LHC physics, as mentioned, Barbara will tell you more in detail later. But I wanted to also remark that CERN is not only accelerator and not only accelerator physics and not only LHC. There are many other projects that are being developed at CERN. For instance, one of the other accelerators, the one that drops its beams inside LHC, is called SPS. Is the one where I said before that was where the W and Z bosons were discovered. Now we use it as an injector for LHC, but it can also be used. The beams from that accelerator some of them are diverted to a large experimental hall. It's what we call the north area. The building 887 is the largest at CERN. I can show you that as well on the map. This is, you remember there are two main sites at CERN. The one I showed you before that looks like a triangular shape, and this is the other one, which is totally in French territory. It's what we call the Prévessin site. And there are many important things in this site. For instance, the CERN Control Center is here. This is where all the accelerator chain of CERN is controlled. We can check the control room here. For instance, each one of these rings controls one of the accelerators. For instance, we can see here all these screens and all these machines are devoted to control LHC, but all the others are here as well, SPS, MPS, and so on. So in this Prévessin site, we have the large hall I was mentioning before. This is the north area. As you can see from the outside, is longer than 300 meters. It's a huge area. And if you look closely here, you can see that the ground lifts a little bit. That means the beams from the SPS are being conducted into the building. And that's what we're doing in this building. The building itself, let me show you this. It has several areas, like 60 areas or so. Some of them are devoted to the test of new detectors that will be used for LHC upgrade or for other experiments. And some of them are dedicated experiments, like to measure the properties of different hadrons, to do dark matter searches and so. I'm going to show you this video. This is a video I recorded myself a long time ago. Not so long, maybe 3 or 4 years. And you can see you can have an idea of the size of this huge building. And I will stop the video when I'm on top of one of the area. You can see this is one of the sides, and I'm going to look at the other side, and you will see clearly. Let me stop here. You see all these pipes here are particle beams that are being dumped into different experimental areas. And in each one of these areas, you are testing new detectors and you are producing new beams of different types of hadrons or so on for some precision measurements. Inside that area, inside of the north area, let's see if I can move to the next slide. Yeah, there is another very important CERN project, is the CERN neutrino platform. Actually, during in this image of CERN, of Google Street View, the neutrino platform was being built here. This is quite old because I think the platform has already 4 or 5 years at least. You can see it was under construction as an extension of this building. Now it's working. And this is one of the efforts that CERN has, one of the projects in which CERN has invested more effort, apart from, of course, from LHC, is a facility designed to the study of neutrinos, to the design of the new generation of neutrino experiment. Now we have there 2 large-scale liquid argon detectors. One of them is Proto-DUNE, the other one is W105, and they will serve as prototypes for the future DUNE experiment in the USA that is supposed to be to start taking data in 2026, more or less. You can see here an aerial view of one of these huge tanks of liquid argon that are being used. There's one single phase, one double phase. You can see how nice it looks. We can take also a look from the inside. Here it is. This is a view of the inside of that red tank. You can see. Let me go and see if there is someone around here so you can see the size. There they are installing. This is supposed to be a large TPC devoted to the measurement and the study of neutrinos. More projects that are at CERN. Let me do this, so otherwise you can see. Not too far from there, we have AMS, for instance. I'm just dropping projects here. There are many more, but I will focus on a few. This is obviously not at CERN. This is the International Space Station, but there is a particle physics experiment installed up there. It is called AMS, the alpha magnetic spectrometer. It has a similar structure to the detectors we have at Collider, so several layers devoted to the measurement of different particles, but it's installed up there. It's a CERN project, and it performs direct precision measurements of the cosmic rays. So before, most cosmic ray experiments are on Earth. So once the particles reach there, have interacted with the atmosphere, and that's of course a burden for those experiments. But AMS is able to detect the particles right up there. And the control room of let me go there. The control room of AMS is right here, very close. You can see this is the AMS control center. And for some reason, things are not working with my connection, but here you are. So actually we are not controlling from Prevesan only the LHC accelerator, but we are also controlling things up there in the International Space Station. This is where all the data taken from AMS is being done. More projects, for instance, this I find particularly mind-blowing. There is another facility at CERN, which is the antiproton accelerator and the antimatter factory. It has a ring, and the accelerator ring that takes antiprotons from the PS and slows them down to very, very low energy, 0.1 MeV. In that way, you can use these antiprotons to perform different experiments to study antimatter. For instance, they are doing an experiment to study the gravitational effect of antimatter to see if antimatter performs in gravity, same as the ordinary matter. They are trying to do they succeeded doing trapping of antihydrogen atoms using the antimatter to do spectroscopy and so on. And this is a very, very interesting project as well. And the antimatter factory is it's in the main campus at CERN, the Meran site here. You can see this is one of the, let's say, one of the top visits for students and for general visitors at CERN. You can see here the platforms from which you can see the ring and the different experiments that are being conducted there. As I mentioned, I'm only using Google Street View and the pictures that you can see by yourself anytime you want. So feel free to walk around CERN and to enjoy the view. Of course, I don't want to offend anyone. I know there are many nuclear colleagues here, and CERN is home also for many, many nuclear physics experiments, other experiments to detect, to measure and study actions, even some experiments to detect the effect of cosmic rays in clouds, etc., etc. I cannot go into detail into all of them, but they are here, and you can. I invite you to check carefully and to see if there are many other things. I'm sure there will be many other things that will catch your interest in the CERN projects. And now I will give the stage to Barbara, and she will tell you more in detail about LHC physics.
Thank you very much, Jesus. So, Barbara, the stage is yours.
Okay. I need Jesus to stop sharing. Thank you. I will get ready with my presentation as well. All right. So in this part, we are going to concentrate just on the LHC project and even more in the CMS experiment only as an example of what can we do as particle physicists at the LHC at CERN. But of course, there are plenty of more things, and this is just an example. And so I also like to start this kind of presentations with these traveling into CERN, so going into the Geneva area in the French and Swiss border, and I hope you can travel together with me and to get your mind into this project for a few minutes. And I also like to start from this slide to present CERN as the European Organization for Nuclear Physics and Particle Physics that was founded more than 60 years ago. During the 60th anniversary, we were able to celebrate and share together the celebration as CERN as a research area, but also as an example of international collaboration. And this is something that is very important. More than 12,000 people working together for the different projects that CERN has associated to. Also like to remind you that since 2014, we have a woman director, general director of CERN. This is Fabiola Gianotti, and then she's going to continue for at least four more years. And so that gives us a push for us to continue in this direction. The first woman as director of CERN, general director. And then given that CERN has the largest and most powerful particle accelerator laboratory in the world, that's what I'm going to try to explain to you today in a few minutes. You're probably familiar with this picture, the history of the universe concentrated in this single figure, where we see the starting of the universe with the Big Bang until today. And so what is important of this picture is the details, right? And so we have a scale on the time and the energy of what happens since the Big Bang to today's life. And you see what we try to produce at the LHC, at the Large Hadron Collider, with these proton-proton collisions and heavy ions collisions as well, is the conditions that happen few fractions of a second after the Big Bang. So you see in this scale where 10 to the minus 10 seconds after the Big Bang, we have produced different particles, individual particles, as electrons, muon, quarks, bosons, and so on, that now is what is making the so-called these building blocks of matter, but that they were completely on their own fractions of a second after the Big Bang. And so what we try to do to also produce with these collisions is the energy, and that happened at these 10 to the minus 10 seconds. And so you can see in detail how after this production of all these particles, then they got in together into protons, and these protons together with the electrons form the atoms, the molecules, the stars, the planets, and our life today, right? And so what we go is to go backwards and try to understand what are the properties and the physical properties and observables of all these different fundamental particles, or elementary particles as they call. For this, we collide protons into each other. And so this is very schematic proton-proton collision. So what you have to understand is these protons are made of different quarks and gluons, and actually what it's colliding in this, what we see is the products of these quarks and gluon collisions. And so this is an example of what's really happening, also shown by Jesus, but in a different way, right? And so we had these proton-proton collisions at the beginning, at the start of the collisions, and what we have is a huge production of different particles to get, for example, from this proton-proton, where we only have mainly up quarks, down quarks, and gluon, we can also, with the probability of producing top and anti-tops, which are the heaviest particles of the standard model. Around these collections, what we have is to use these detectors, and which we consider that the cathedral of the high energy physics, right? And if you have the opportunity to travel to CERN and visit CERN, make sure that you are allowed to also go down to the caverns if they are under maintenance. For example, this period that we are right now, the experiments are stopped. We don't have protons around the LHC, and so that they can be visited down in the cavern at 100 meters underground. You will have a similar view of this picture, where we put all these detectors around these collision points, and they are made of different sub-detectors. And so these detectors are where we have at the collision points, and they are divided in different layers, in order to understand, identify, and measure the different particles that are produced. And this is just a quadrant of the CMS detector. Is the transverse slide through the CMS detector, in order to you to understand what happens, each of the particles that are produced in the detector that can be identified. So for example, we have the tracker system and the electromagnetic calorimeter, in order to measure and see the electrons in the red line. So they produce a signal in the tracking detector, and they deposit most of its energy in the electromagnetic calorimeter. We can distinguish them from hadrons, for example, protons, neutrons, or other particles, which they will also leave and signal in the tracking detector, and then they will deposit of the energy in the hadron calorimeters, or muons, that are these minimum ionizing particles at this given energy, where they travel the whole detector and from the inner part, the collision point, all the way outside the muon spectrometer, or the muon chambers. And so this is a way that we identify the different particles that later we can analyze and reconstruct from the physics analysis. So this is a view of what happens when you have two proton-proton collisions in the center of the detector. And so this is a Higgs candidate. This means that we have reconstruct the event. This is a real CMS data collected in 2012, where the proton collision happened at about 8 tera electron volts, and then from these collisions, a Higgs boson is produced, and very quickly this is decayed into 2 photons. And this is what, at the end of the day, what we see in our detectors, the 2 photons that leave some energy in the electromagnetic calorimeter, and they pass somehow invisible to the tracker, because they don't have charge. And but this is an example of the 100,000 millions of examples that we have in the proton-proton collisions in the CMS. One of the topics of studies is the mass of these elementary particles, and we see and we don't understand the different masses of them. Why the quarks among them, or the leptons among them, they have such different particles. In this schema of the particles, we see the up quark, the down quark, the bottom. We see the charge, the S quark, the bottom quark, and then there is one missing quark, which is the top quark, which is the heaviest particle that we know. And then we understand that the different masses is basically related to the systems of this new particle that was discovered in 2012, which is the Higgs boson that makes basically relates the Higgs field with the Higgs boson particle, which is given mass to these different particles. But the nature of the different masses, the hierarchy, and the different conditions that these particles are in, is not understood yet. And then we are trying to understand this kind of topics in the high energy physics field. I used to present this Higgs discovery as the biggest discovery in the last 50 years, but now I prefer just to present it as one of the biggest discoveries, given that also during the last year, we've seen gravitational waves. We have seen the picture of the black hole. We recently also saw the latest results from Fermilab in the μg2 and so on. So certainly it's a big discovery, but it's amount of one of the biggest discoveries of the last 50 years. This was awarded with the Nobel Prize for the two theorists that predicted the existence of this Higgs boson. So in the picture, you see cheering with a beer to Peter Higgs and Francois Englert, together with the previous general director of CERN. And this picture is taken in Oviedo because we have here in the city of Oviedo a very prestigious prize that it's called the Prize of Asturias, and this was not only given to the two theorists, but also was recognized to the two experiments, CMS and Atlas, that made this discovery possible, that basically discover the Higgs boson and measure its mass. So not only the Nobel Prize, but many other awards have received this Higgs boson discovery. And so how does this data look like for us, for the physicists, for the high energy physics? And I found this PhD comics figure that kind of summarize our effort. So we take years of data taken. So this Higgs discovery started, the Higgs measurement started in 2010, until 2012, with plenty of effort and data from the different experiments. So it takes years for the data taken. It takes also years to try to interpret this data, and then it takes about some amount of time also to write it. And at the end, we just have a single plot or a single figure to show what all this data summarizes. And this is how the data looks like for us. And this is a plot that if you are not familiar with this kind of the presenting of results you will get through your PhD and so on. So this is a figure that shows the number of events as a function of the mass of 4 leptons, because the Higgs boson can decay in different type of processes, but one of the candles of this Higgs boson is the 4 leptons of 4 muons, 4 electrons, 2 muons, 2 electrons, and so on. And so we present this result as the events as a function of this 4 lepton mass, in order to show what's the expected number of backgrounds and what's the expected number of signal, and how the data agrees with this. So if I show this again, you will see on the top of the figure, you see the data. So this is the data taken in 2011, 2012, how we are adding all this data together, which is the black points, and how accordingly we are scaling the simulation, the expected background in blue, and then the signal. And we see how this data will only only be understood if we have some Higgs boson at this 126, 125 GeV mass that can explain this so-called data excess or so on. So you need years of data taking, plenty of tools of physics analysis in order to understand what's happening. And basically this is the best scenario, right, where we have we are looking for something where we kind of expect to be a difference between the data and the prediction. And see, this is how the data looks like. The Higgs is not the end of the story. Of course, it's a very important piece of the puzzle for the standard model, but we know that the standard model does not answer all the open questions that it has. And one of them is, for example, the origin and the candidates for this so-called dark matter. And so we know, and thanks to the pioneer Vera Rubin, we know that the rotation of the galaxies are not as expected as we have from the visible data. And this is an example how the velocity as a function of the distance from the center of the galaxy was expected to be get smaller and smaller as a function of this distance from the center. Instead, what we see is that the velocity increases or stays stable at some point. I think I have here a link to Wikipedia that shows, and with this I finished, that basically, I'm going to stop sharing to show you my screen. The screen, yes. Simply to show you how this looks like. Oops. How you have a simulation on how you expect this stable somehow, this stable velocity in a galaxy where the rotation is faster in the center and then slower in the outside. Instead, what we really are observing is not that, but we have a velocity which at some point far enough from the center, the velocity is kind of stable, and we will see something more similar to the picture on the right. So that's all I have for now, and I also wanted to leave some time for questions from the audience.
Thank you very much, Barbara. Thank you very much for this great presentation, where you have really, both of you have really shown that CERN is one of the, well, is the largest facility, right, in the world, and many things are going on, and many exciting things are going on. I hope that many exciting things will keep going in the future. Now, questions. If you have questions, you can raise your hand or write it, type it in the chat directly. So please go ahead with questions. Let me see. Or write it in the chat if you think it will be easier. So, do you have questions? If not, I'll ask them. No problem. So yeah, I have some questions to both of you. You have talked a lot about now, and I think that also yeah, there is one. What would you comment on a fermion existing at a mass with a mass higher than the Higgs mass? Okay, so this goes directly into from the Viruta Kahan. So what could you comment on that? Imagine that I mean, there is a fermion existing with a mass more higher than the Higgs mass. So
I cannot see the question. Is it in the chat or?
oh, they have written. I mean, they have written. Oh. I will write it.
Anyway, no. A fermion higher than the Higgs mass. Well, one of the precision measures that was provided not by LHC, but the previous accelerator that was installed inside of the LHC tunnel that was called LEP. It was an electron-positron collider. One of the most astonishing results that the accelerator provided is that within the standard model framework, is only possible to have 3 families of fermion, 3 generations. So if something like this exists, it would be some kind of a hint of exotic physics beyond the standard model. These kind of new particles are being searched at CERN, at LHC. So, and every kind of exotic signal you can imagine is being searched at CERN. So far, we haven't found anything. But of course, we will keep looking. And that's one of the important points that, towards in favor of continuing the LHC program and increasing the number of the luminosity, which is the number of collisions per second that we will be able to reach, in order to see if something that it might be not very frequent, but it might be there in nature is existing.
Yeah, thank you very much. He's asking about the top mass.
I'm asking about the top.
I think I misspelled the question.
The top quark is observed. It was discovered in 1995. So I'm not sure what the question is exactly. Would you like to rewrite your question?
Yeah, probably would be better because we don't really understand.
Yes, maybe I wasn't clear. What I show is the fact that we have different fermion masses is is basically just understanding how they interact with the Higgs field through the Higgs boson and so on. And the fact that this mass is higher than the Higgs, isn't that weird? Yes. It is actually, and it's not only that it's higher than the Higgs, that is much higher than any other fermion that we have in the standard model, and so it's more than 100 times higher than the bottom quark, which is the fermion in the same family as the top quark, and this is not understood.
Yeah,
it's not clear. We know that actually the coupling of the top quark and the Higgs is the highest, is the biggest with respect to the other fermions, that we know. And so it's expected somehow to have a higher mass than the other given the coupling, but the value itself is not understood, no.
Yeah, I agree. So more questions? Interesting question, though. Thank you for the question. So more questions? Let me see. If not, if you don't want to talk, just question. Except for electrons and muons, you can see taus at the detector?
Yes, we reconstruct taus. Taus is a much more difficult lepton. So electron, muons, and taus are these type of leptons. And so basically, yes, we can identify, reconstruct taus. They quickly decay into electrons or muons or to hadrons, and basically that's what we see, the decay, the decays of the tau leptons. But of course we see. The only thing we cannot measure at the CMS detectors are neutrinos. Sorry, I forgot to mention that before. And from all the elementary particles, the only see that we don't measure or see in the CMS detector are neutrinos, because they pass completely invisible to us, and we infer the energy and the momentum through energy conservation, but we cannot see neutrinos. They don't interact with matter, and so they don't interact with any of the pieces of our subdetectors.
So there is another question. Is there any possibility that Higgs can have a mixture of CP-odd?
That can have a mixture of CP-odd?
Yeah.
Actually, yes, we are. I don't know what's the conclusions of that, because I'm not following closely, but we do. We actually do these kind of searches at CERN as well, at the detectors, and so we have dedicated measurements for CP-odd and CP even in the Higgs sector. But what I cannot answer is what's the conclusion so far, because I don't think we have anything finished on that end yet.
Very nice question. I didn't know the answer, by the way. I mean, I didn't have a clue. No, they cannot be measured.
No, that's my, I was answering to Fang, because
I mean,
he was also asking if we can be, if taus can be measured directly in
yeah, they really decay fast, super fast. So, I mean, yeah. Sorry, I didn't understand that was okay. That was really one answer. More questions for Barbara and Jesus? I do have one though. Well, I do have two if I can. So one is, well, if you want to keep writing and keep asking them, but my question is, how do you see CERN in the future, in like 20 years from now?
ourselves. You mean ourselves?
You will be there for sure. I know, but what how do you see? I mean, what do you think it will be? Well, now we have LHC for like how many years more? Even in the high luminosity.
With the high lumi, I would say at least 15 years of LHC taking data.
Okay.
I don't know. This is more a personal opinion. The field is in a crucial point nowadays, because we are seeing a lot of results that are evidences of where the standard model is failing, and all these new results added up should point us to where new physics could be found. So it's still early. There are many projects, as you know, to build new accelerators. Like linear collider would be a lower energy regime, but a more precise machine. But there are other projects that are already starting to think about building a super collider already at CERN. Instead of 27 kilometers, it will be a huge machine of 100 kilometers. It will be the FCC, the Future Circular Collider, colliding particles at around 100 TeV, the center of mass. And this will not be built in 20 years. If it's in 20 years, probably I will not see it. Maybe Barbara will be will be alive still to see that. But the good thing about this field is that, and you all know, it is very dynamic. So we can easily, let's say, adapt from one domain to another domain of experimental physics. What I can only tell you is that I see myself still doing research and trying to expand the knowledge of physics. In terms of projects, hopefully, still collider physics will be, not for sure, will be alive in 20 years. It depends on how technology evolves, but it's a rich field.
So there is another question. Do you have a simple way to explain to non-physicists the meaning of 5 sigma discovery? Okay, so the meaning of a 5 sigma discovery. Even if now that I'm in cosmology, 3 sigma to me is already a lot, but I know that so 5 sigma discovery. What's the meaning?
Why can't I see all these questions?
Yeah, the allowance that last question, I don't get it. But anyway, 5 sigma discovery, it's basically you have to translate 5 sigma into the probability, into a probability of not having anything else that is not the signal you expect. For example, in the case of the Higgs boson, a 5 sigma discovery means that 1 over, I just don't recall the number exactly, 1 over,
I think it's 3.5 or whatever, 1 million or something like that.
1 million to have this signal Higgs over anything else, over what we call background. Basically, it's the probability of having the signal plus background with respect to only background, let's say. I think that's That's the easiest way to explain it. So to have the highest probability of seeing what you expect in terms of signal.
And then another one is, can you say something on Higgs self-couplings? What its importance and implications about the Higgs self-couplings?
Basically, what I mentioned is this relation between the mass and the Higgs boson and the Higgs field, right? And so we have to prove that the Higgs couples to itself in order to also have its mass from it. And so at the same way that the other particles, the other fermions are acquiring their mass through the Higgs field, through the Higgs boson, then we have to explain it. We need to explain it also for the same way. So it's completely important to be able to measure the Higgs coupling to itself to just explain all, or to basically extrapolate to the other cases as well. So it's crucial for us. It's crucial to be able to measure also this coupling.
Yeah. I mean, to understand the whole thing, you have to understand each of the pieces to understand the whole picture, right? So I mean, anyways.
So maybe you want to answer also this question that says with the signal of neutrinos. And
yeah, how can we know the unseen particles? Actually, one of the most important features of a detector is that it should be hermetic, because what we do in CMS, in all the collider experiments, is to reconstruct everything that's happening. And since we know the collision energy and we can reconstruct it very precisely, we can deduce when a particle has not been measured, like a neutrino, because you reconstruct the balance of energy and you know that energy is conserved. So if there is a large pool of energy in one direction, and for instance, for us in CMS, it depends on the magnetic field and stuff. But if you see that some energy is missing in one direction, you can infer the presence of a neutrino and say that the neutrino was taking the energy in that direction. So that's it's very important. It's very important that our detectors are compact and hermetic, and that's the way to reconstruct neutrinos, because as Barbara said, we cannot measure them directly.
And to say how can we know that we have neutrinos or physics beyond standard model, we test it through simulation. Basically, the neutrinos is a standard model particle. We know how it behaves. We understand it through simulation, through the detector, through this missing transverse energy, and we basically know exactly what distributions we expect from neutrinos. Anything else that is beyond that, or anything else that doesn't agree with those distributions, can be attributed to beyond standard model physics. So any deviation of the expectation can be basically given as exotic physics beyond standard model, whatever you want to call it, and that's what we use. Because at generator level, let's say being a bit technical now, but I think most of you can understand it. We know what a neutrino is, and we know how we know what to expect from it. Also from many other beyond standard model predictions, right? And so we compare our data and our expectation with all these beyond standard model predictions.
Okay, and now I think that we can finish with this question. So which lab observation, which is quite exciting, which lab observation is most likely a sign of new physics in your opinion? So I mean, I guess they are meaning, for instance, we have LHCb, right, results. We have also G-2, right? So what do you think, in your opinion, which one is the leading one? Let's say they could be none, or they could, but the most compelling one, let's say this way, that you think that it could be a signature of new physics.
Well, as of now, the G-2 is more significant, because the signal, the new signal LHCb2 that questions lepton universality is at 3.1 sigma or something like that. That sometimes disappears, unfortunately, but 4.2 is quite a lot. There's a sign of new physics that has been there for a long time, which is, for instance, the neutrino masses, and that's a sign of new physics. The problem, let's say, with these results is that we know there's new physics beyond the standard model, but we don't know where to look at yet. We need clearer signals and clearer indications where to go for.
Barbara, in your opinion?
So in my opinion, I have two ideas. One is whatever happens harder or in higher energy scales, let's say things that can show up at the tails of our distributions in the particles that can have 2-3 tera electron volts of mass. That would be definitely a sign of new physics. And also searches on supersymmetry particles. So that can explain dark matter candidates, neutralinos, and so on. And we do those kind of searches at the top sector and the electroweak sector, like searching for electroweakinos, charginos, and all this. And then for me, basically, this kind of sign of new physics in that area, it could show up completely a new area, because this means that we have another 24 new particles, right? So that we have to search for.
And to identify, yeah.
Mm-hmm.
Anyways, so we finished the session here. I would like to thank again a lot Barbara and Jesus and Barbara, for your wonderful presentations and for the time you have devoted to this. And of course, for the nice work you are doing every day with passion and effort and scientific and completeness that you are doing. So, I mean, thank you very much to both of you. Thank you a lot also to the assistants and also for the questions. And see you whenever, and to the others, see you next week with the CMS virtual visit. So we will go down to the cave, let's say this way, with Oscar. Okay. So
Thank you very much, Olga, for inviting us, and enjoy the school, everyone.
Thank you. Bye. Thank you.
Thank you. Goodbye.
Bye.
Bye.